Welcome everybody. So my name is Tom Knechten. I'm working at the Siemens Simcenter team. I'm the product manager for all the exciters that we have in our portfolio, the inertia shakers or the acoustic exciter. We have a couple of slides that I want to show you. It's all about the FRF measurements. Next to all the operational testing, FRF measurements form a large part of the time we spend to understand the acoustic or vibration behavior of automobiles, aircraft, machinery, other equipment. This type of data, it has not so much to do with like the environmental conditions we have outside or with the operational conditions of an electric motor or an engine, but still it requires a lot of attention to many different details. So I hope also during the presentation that I can show you some of the tips or tricks that we use to get the best FRF possible in a given time frame, of course. So we will mainly focus on the exciting part of the FRF measurement and less about the microphones or accelerometers, the strain gauges, the sensors that are used for the typical response measurements. Now, to get an idea on why we are looking at those dedicated exciters, we also see some trends or challenges that you may also relate to. So either we have ever less time to perform a measurement, or simulation colleagues would like to get more and more accurate test data to correlate their CE model with. Could be that different engineering centers need to transfer test data, which needs to be relied upon in terms of measurement uncertainties. So there are all different trends ongoing, which maybe put more requirements on the test results that have been collected. To answer to those trends, Simcenter portfolio consists of a series of acoustic and structural exciters that make the FRF testing typically more efficient, also more accurate. We have these type of exciters to cover a specific frequency range with sufficient output. All of them are also equipped with internal reference sensors, which serves as reference for our FRF estimation. And acoustic exciters, they should produce noise and should not couple too much with the structural part of the system that people are testing. So there should be no vibration transfer. For the structural exciters, there we would like to generate vibrations in one direction at one location, but we want to reduce the noise emission as much as possible. For the coming slides, I will show you an overview of the different exciters that we currently have. We also expanded our acoustic exciters portfolio, so that would be also one of the topics that I want to show you some features and characteristics about. And I think it's also interesting to understand what challenges there are in terms of the high frequency FRF measurements, because, well, at least we hear more and more that people are interested also in the high frequency part of the structural dynamics. And I think I can also share you some interesting results. Now, within the Simcenter portfolio, we have a couple of bigger topics or bigger paths that companies use to evolve upon. And when we talk about model the complexity, at least in my transfer path analysis background, I think about that type of methodology or analysis. So which is a concept used across the NVH community. So it may have been developed in marine or automotive industry, but over time we see it coming back in all sorts of industries. And that method enables to characterize, understand, and eventually troubleshoot also a complex system, which typically consists of many different sources. And the data used for that are a bunch of operational data while that machine or tool is operating, but it also consists of many different types of transfer functions. And to enable the end user, the engineer, to measure those, we also have a very dedicated set of structural exciters. And here you see some pictures of an exciter which is mounted in the 3 different directions on an interface location, or the number of paths that people would like to investigate increases every time to higher numbers. Then we also need to think about how to capture those transfer functions in a time-efficient way. For enabling the insights, it requires, like I said, excitation at locations which are sometimes difficult to access. And what we see here in a sketch is actually a lineup of 3 different excitation possibilities. And so in the back, you see the white classic shaker, which requires a support. You need to be able to align the armature with the stinger, with the force sensor, with the test object. So it does require some time to get a nice alignment with the structure. And you need the space to position that shaker. If you look in the middle, we look at a typical modal hammer with a force cell in the tip. So that works fine. Of course, it impacts angle or orientation, the impact location. It also depends on who is operating that modal impact hammer. You can also imagine that in many situations, impact measurements are done by 2 people. So one is somewhere hitting the structure. The other user is checking the data on the laptop in the data analysis software. In the front, you see the inertia shaker, so the integral shaker in this case. Typically, we mount these by a direct glue connection. And because those shakers are self-aligning, wherever we glue them in, it doesn't matter which orientation, they're always practically perpendicular mounted to the structure. So also the force generated is along that axis of installation. And that helps people to prepare their testing. They can also describe the installation location and orientation in a very easy way using that integral shaker. I think also a differentiating element between these 3 excitation mechanisms is also the variation that is visible or that is present in the transfer function measurement. When different people are using that equipment, and we see here an overview of the hammer, conventional modal shaker, and the integral shaker. You see that we can vary the position, the angle in some degrees for the different exciters. Actually, they do have an effect on the final result. And the final result is the transfer function. And in this case, that study was done on a twin body where the excitation location was near the transmission mount of a passenger car vehicle, and the response was a occupant ear location. So and here you can see the variation, the minima or the extreme values of the FRF amplitude of that vibroacoustic FRF measured with the different exciters. The top one is then the result of using the integral shaker, where mainly the positioning can still vary. The middle one is then measured using the conventional shaker, where you have to deal with the external support, with the stinger alignment, the force cell alignment. And the bottom one is the modal impact hammer, where the impact angle, location, the variation force amplitude may cause a larger dispersion of the amplitude and phase as well. Now, the smaller your variation, the more accurate your predictive models could become. In terms of time, so accuracy, I would say that's one of the elements. Accessibility is important in selecting an exciter, but time is also definitely important. I think there's a general trend that the number of physical prototypes is reducing. People try to build models in analysis software to predict what noise or vibration behavior will be whenever the product is physically assembled together. But still, if physical testing needs to be done, it needs to be done in as short time as possible. And the fact that the acoustic exciters, for instance, they are compact, but they still include a reference sensor, it allows for a relative fast installation of the source. You have to put the source in a way such that it doesn't couple structurally with the test object, but then the rest goes in defining all the signals that you want to send to the source to excite the structure. And that's about it. Of course, you have to check your data afterwards, but then you can dismantle it. So inline calibration or calibration on the spot is typically not necessary. So that also saves some time. Compared to the structural exciters, I think I talked about it already a minute ago. And so compared to the classic shakers, the inertia shakers that we can directly mount to the test object really saves a lot of time in terms of installation. The hammer test, it goes very fast. So by using an impact hammer, the setup should go very fast. I can imagine that sometimes validation after the data collection makes end users to repeat some hammer testing when they don't have enough confidence in the data. There we see also a difference in the validation phase of after the data collection. connecting all the activities. For instance, with the transfer path analysis, we need to combine all different data, but we need to excite at really a lot of different interface locations and orientations. A typical example from automotive, when we would like to excite at the chassis body interface connection of the top strut mount. And so you see on the lower left some body there where the shock absorber coil spring assembly is mounted into the body. That's a very typical example where space is quite some job blocker, I would say, because with hammers you don't have any access, or hardly any access, at least not in the 3 directions. And with the larger modal shakers or conventional shakers that need an external support, like the vertical direction could be an option, but the lateral directions is way harder to excite at those locations. Now, for that, we also have some solutions where we do not exactly need to excite in the 3 orthogonal directions, but where we could measure under different known angles, and then using Tesla to combine those angled excitations in order to reconstruct the global X, Y, and Z inputs back. That would also help people in order to get the FRF data that they are looking for. This tool does not only help in that location, we also have other interface locations where this can be very useful. Now, a typical example of the series of measurements that we are doing can be seen here. So we see here about 7 different pictures of the same structure, but where we installed the integral shaker, so that inertia shaker, at different angles. So you see here that the shaker, after each FRF measurement, is removed and actually screwed or installed under a different angle. And that is done by using this very small adapter. So it's a lightweight adapter that can be also glued to the structure. On top of that, the shaker is mounted. While we are knowing all the different angles, we can use that geometric information and reconstruct the inputs as if the shakers were mounted in the X, Y, and Z direction. That is not only the physical data collection, or it's not only a matter of measure the data like you see on the pictures, but Tesla, or the processing software, also now allows us actually to grab those angled FRF data and process the transfer functions to X, Y, and Z direction in one fluent flow. That principle, or that idea of reconstructing transfer functions to points where we normally cannot excite, was also covered by the virtual point transformation topic. So that virtual point transformation is also a solution to excite at locations around the desired excitation locations. The next slide should give you an idea of a rim or of a tire rim assembly. Imagine that we would like to excite at the center of the rim. We don't have any space there because also the wheel knuckle is located there. Then virtual point transformation can be used still to capture those transfer functions and reconstruct them as if it was excited at the center of the rim. Those are tools integrated in Tesla that helps users get the data that they are looking for. And so we insert, in this case, an example of wheel center transfer functions. We have a selection of accelerometers mounted on the rim. We have some locations designated for excitation with an inertia shaker. Choosing different angles, different locations, we build up a set of equations which can later be used to derive the X, Y, and Z, but also the rotational input at the location where we want. After that reconstruction, then there are also tools available that allows you to do some data quality checking. Now, as an overview, we talked about the different exciters. Here you can see an overview of the acoustic exciters. So sources that emit noise, that have a reference sensor built in, that outputs this emitted sound source strength. We go as low as 10 Hertz, and we go up to 10 kilohertz or even beyond 10 kilohertz for measuring transfer functions. So noise, they can make even higher frequent, but also to capture transfer functions that also accurate. At this moment, we go up to about 10 kilohertz. And I will show you some examples where we compare that data with some other transfer functions. Looking at the structural exciters, then we also have this time 4 different inertia shakers. They vary in size, they vary also in output. So typically the bigger the shaker, the higher the force output, but also we see a limitation then in frequency range. So you see that we have to have smaller shakers, which are dynamically more stiff, in order to cover the higher frequencies there as well. Those shakers, they are very compact, but still they do include a very unique feature, and that is actually our inertia suspension system. So in between the stinger, which I should be able to point at with my mouse. So inside we have a stinger. Then we have the inert mass that allows us to generate a force entering the structure. But between the stinger and the inert mass, we have actually a very soft suspension. A very soft suspension in the 5 degrees of freedom. So the 2 translational and the 3 rotational directions. And that actually allows us to reduce the mass loading of the shaker. You can imagine the shaker, like we see here, it weighs about 350 grams. You don't want to rigidly couple that to your test object. Not only the mass will affect the structural dynamics of your test object, but also the possible internal shaker modes will also have an effect or will be measurable by accelerometers, by strain gauges, that will result in an inaccurate transfer function. So that decoupling suspension makes actually that the only mass that the test object is receiving or is connected to is the internal stinger. And that is really limited for this shaker. It's limited to like 20 grams. But of course, at 0 hertz, you have the full weight or the full gravitational force acting on the structure. But from the first rigid body modes of that inert mass on the stinger, the structure will only sense the small mass of the stinger plus the stiffness of the internal suspension and the damping of that suspension. But that's a solution that allows us actually to excite the structure without the structure actually feeling the whole shaker with their modes. So for this shaker, the bigger one with the internal decoupling suspension, so we are using this one up to 2000 hertz. But of course, we also heard that 2 kilohertz is not our frequency range of interest anymore. People want to understand the structural dynamics way higher than 2000 hertz. So we also have exciters for that. And to show you a bit the application on a component, an electric motor, we have some measurement setups that we can share right here. The picture that you see here shows actually a setup of an electric motor with a gearbox connected to it. The rotating parts like bearings and the rotor, they had been removed, but the stator with the windings are still inside, and the housing is as you see it. So it's suspended free. We also added 2 high frequency shakers and 2 accelerometers on that structure. So on the red circle on the right, we see a shaker in the green direction, while the top red circle, it shows a high frequency shaker exciting in the red direction if you look at that coordinate system. And that allows actually to measure structural transfer functions from one shaker force sensor to the other accelerometer response and vice versa. So let's have a look at those results. So basically with 2 shakers and 2 accelerometers, we can measure 2 transfer functions, assuming that that assembly behaves in a linear way and is also time invariant. Then basically those transfer functions measured from shaker 1 to accelerometer 2 or measured from shaker 2 to accelerometer 1, they should be identical in terms of phase and amplitude. Here you see such a comparison. So we look at a transfer function displayed in a Bode diagram. So the top part is the amplitude in function of frequency. So we start looking at it from 200 hertz up to 10,000 hertz, where the red transfer function is the FRF measured by one shaker, and the blue one is the same FRF measured in the other direction. Actually, this gives us an idea of how accurate or how much the shaker is influencing the structure, assuming that the test object that we are testing is linear. And in this case, I think even up to 10 kilohertz, the match is really looking nice. We can even zoom in to the lower middle frequency range. So here we are we zoomed in from 200 till 4000 hertz. And also here you see that it doesn't really matter at which location we are exciting, the result is the same every time. So those very small shakers, they are weighing, the total weight of such a small shaker is about 30 grams. The mass loading is about 3 grams or even less, but it can still excite an assembly like you saw right here. So that mass was about 30 kilograms. So that's a very big difference in mass, but it can still produce very high frequent structural transfer functions. Now we compare two shakers and two accelerometers, all of the same type. So we can do that exercise. So comparing a direct and a reciprocal FRF, also using different equipment. So second exercise we will see here is where we've put the assembly, so the electric motor gearbox assembly on floor in a semi-anechoic room. We put it still on support to get some free conditions. And we also measured in two directions. So the left picture, like you see here, is actually the setup where we excite with an acoustic source towards an accelerometer on the structure. And the right picture shows actually the same FRF measurement, but in an inverted way. So there we have a high frequency shaker very close to the accelerometer, and we measure to a microphone which is at exactly the same place as where that acoustic source was in the first measurement. And the FRF data should be, at least in amplitude, should be the same, and in phase it will be inverted by 180 degrees. If you look at that result, and in this case, the frequency range is 200 till 15,000 hertz, so it's a bit higher than we normally use. But you see actually that for both measurements, the top picture is the FRF amplitude, the quantity is Pascal over Newton, and so force input, microphone output. And the lower picture is actually the coherence, which says something about how much of the output is correlated to the input. 100% coherence means that all of the output is defined or determined by the input. And for the main frequency range, coherence is really high, so it's above 80%. So that looks very good. Low frequent, of course, we are looking at a vibroacoustic FRF. So that also depends on how well that assembly is radiating noise at low frequencies. And I think at those global modes, the global bending or some torsion, the radiation efficiency is maybe also not so great because the wavelengths are still quite large. This also adds to the validity of the high frequency shaker measurements. So we can use that very small shaker and add it to a component without disturbing its structural dynamics significantly. And that helps users then in the end to use that FRF data measured by that high frequency shaker to compare that with simulation models or results or force response functions coming from simulation. And these are typical results where people would like to understand how well they are close to reality. And typically that type of correlating models and updating models, it goes in different steps. They typically start on component level, see whether the modeling method has been correctly chosen. And then they start to assemble parts to understand which connections have been modeled correctly, etc., and making it more and more complex. The match that you see here is a structural transfer function in the frequency range of about 200 till 3000 hertz. And this allows people then to make decisions whether they need to increase the realism of their modeling or if they find it acceptable. Now, just about the size. So the measurements that we showed the past couple of slides, they have been measured using that high frequency shaker on the top left. So those are all structural shakers. As I said in the beginning, I also wanted to show also some new product, and that is an acoustic exciter. So it's a monopole source, but which is actually very, very small. And so it's a source really meant for the lower to mid frequencies, so say 40 hertz up to 2000 hertz. So it needs to produce low frequent noise, but at 2 kilohertz, we still wanted it to behave like a monopole source, like a point source. So a microphone is a point receiver. Here we want to have an acoustic source which behaves like a point source. And if we compare it to the existing lineup of the different exciters that we already have, then on the left side, you see the big brother basically of the miniature source. So that's some source that we use for FRF measurements of larger structures or larger cavities. But if people would like to excite cavities which are smaller than a shoebox, for instance, and then that most left source is still on the larger side, I would say. The most right side, yeah, there we have a source which is not a monopole source, it's not intended to be a monopole source, but it's a source that mimics a human torso. So instead of having microphones at ear position, this is a source where a noise is generated at the ear location itself. So that's really a source meant for reciprocal excitation at occupant seat location. Now, looking at the QIND, of course, it's the smallest of the three. The low frequency noise generation happens at the central part by two domes which are moving in opposite phase. It's, in terms of diameter, about 1 inch diameter, and in length it would be about 4 inch long, I would say, a little bit more than 4 inch. And the sensor cables and the voice coil cables, they come out of the sides or the top faces of the source to avoid that we influence the noise radiation from the central part. Of course, we need to somehow fix it at the location where we want to excite. So there are also some fixtures or mountings available. But let's have a look at the noise emission. So actually a few hours earlier today, as my colleague to see whether we could visualize the noise emission location. So we are generating some broadband noise up to about 5,000 Hertz. And we are now displaying the noise, well, while that source is being excited. So the top left picture, that's the most interesting part. But because of the color map, it was difficult to see where the source was. So that's what you see now also at the top. But it shows that the acoustic center, if you wish, is also lying really at the center of that source. So looking at some typical examples of data, then we also get back to the body noise transfer function. So this is a very typical FRF measurement. Of course, it is a source meant to generate low frequencies, but still it is a very compact device. So that means that the radiation efficiency, so how easy can we generate low frequent noise, is very small, so to say. So the radiation efficiency is small. That means that, yeah, we do see limitations in the lower frequency range to measure transfer function. So I want to share here an example, and to understand or to get a feeling a bit on what type of transfer function or what do we need to expect or what can we expect for a fiber acoustic transfer function. We did the same measurement again with the integral shaker in this case that we can use as a reference. So we measured the transfer function between a subframe connection location at the rear of the vehicle, and we measured to a microphone inside the passenger cavity. So we measured that again in two directions. The right curve is the amplitude again of the fiber acoustic FRF. The blue one is the one measured with the miniature source, while the red curve is then the reference curve, if you wish, measured by excitation with the integral shaker at the subframe connection point. So in this case, well, we could even choose whichever FRF we would like to use. There are some narrow band differences, but overall the trend is very similar and actually even very low frequent. I must say that the miniature source FRF, so the blue one, is really still matching the integral shaker result. I do expect that also different locations or different vehicles, yeah, that's below 100 Hertz, the miniature source may not be powerful enough for exciting that type of system FRF. But in this case, it worked out very well and it matches really, really well with the integral shaker. And so the differences that you see, so the y-axis is displayed in decibels, so in dB, and each horizontal line and the grid line is 5 dB. So the variation could be in a few dB only between the reciprocal and the direct FRF, which is, I think, pretty good result. Now, it is a very small source. You can even fit those type of sources also in very small areas where normally you cannot fit the larger loudspeakers that we have. I think this should work. And so the left one, it works to excite the car cavity, but it will not fit, for instance, underneath the car seat, or it may fit in between the body floor and the car seat, but because of its size, it may show some diffraction effects in the FRF. This miniature source, so which is now located in the red circle, it will have no real issues with fitting it in those small cavities. Looking at a typical acoustic FRF, should become somewhat bigger than the FRF measured here. It starts from about 10 Hertz up to 2000 Hertz. For acoustic model analysis, typically we are not interested in frequencies above a few hundred Hertz. So we stopped exciting at 500 Hertz. So that's why you see that the coherence drops above 500 Hertz. But below, you see that the coherence is pretty okay at some anti-resonances at 280 Hertz, 380 Hertz. You see some dips in the FRF. And there you also see that the signal to noise ratio is not ideal. And that's where the coherence will also collapse. And then also low frequent, you also see that the coherence drops. But that could also be a combination of a limited output of the source, but also the microphones should also still work at 10 Hertz, of course. It could be that the microphones used, like the half-inch microphones, that they are not always performing perfectly at 10 Hertz or even a bit lower. Now, the coherence is something very relevant when you do your measurements. You would like to get your coherence as high as possible. But another way to increase the quality of your FRF or the stability of your FRF is by increasing the number of averages that we take. I think with impact hammer, you will take 5 averages or 10 averages, but that's about it. With shakers and sources, you can take almost as many averages that you want. By increasing the number of averages, the coherence will not so much increase. It will stay the same because the signal to noise ratio doesn't change. But the FRF stability or standard deviation will definitely decrease when we take big steps in the number of averages. So it's not a matter of 5 averages or 10 averages, but it's about 10 averages or 100 averages or 20 averages and 200 averages. Then you will gain a lot in reducing the standard deviation on your FRF. So the source itself, it's meant for the lower frequencies. Of course, we have typically an interest also for the higher frequencies. So what we see here is a comparison of vibroacoustic FRF measured by the 2 devices. So on the one hand, that should be the blue one, is measured with the miniature source. We measure from ear location to a subframe connection location. The red curve is measured by that high frequency source. So that compression driver with the tube source put at the same location at the ear. And then you see that we can measure both the low frequent part, the blue part, and also the high frequent part using the data from the red source. And you could decide, okay, that this is it. And we either choose the blue FRF or the red FRF, depending on my interest. Of course, you can also combine these 2 FRF functions by using the data calculator in TestLab in this case, or there is also that external FRF merge tool that actually helps to make one block out of the 2 measured transfer functions. And that will help you actually to get rid of one block that you don't need anymore. It will combine the red and the green curve in this case, such that you will have a transfer function starting from about 20 Hertz with acceptable data quality up to 10 kilohertz. That way, you can also choose, like it's shown here, you can choose in which frequency range there should be a transition from red to green curve, and then the result can be stored in the same project in this case. And you can drop the 2 separate transfer functions and keep on using the merged transfer function. So I think that's also something interesting to check out in case you are using different exciters for different frequency ranges. Another application that could be interesting is actually the acoustic transfer path analysis variant or equivalent, which is actually the airborne source quantification. In this case, we see the source close to a ventilation opening of an HVAC system. The local transfer functions that are shown by the blue arrows on the left, those blue local transfer functions could be measured by this type of source. And that enables engineers to quantify the noise emitted from such a duct. And that could be interesting for predictive modeling. It could be interesting for troubleshooting as well. But for those near field acoustic transfer functions, this very small source is really well suited. It will not disturb the acoustic environment because the size is way smaller than the wavelength that it emits. and it's powerful enough for those local transfer functions, which are in the vicinity of, say, 2 or 3 feet away from the source itself. So that could be an interesting application or use case as well. But since these FRFs are very close to the acoustic FRFs that I've shown with the acoustic model exercise, it's not really necessary to show that again. So in general, I think most of the elements that you see here, I talked about already. So we do have some supports that comes along. All the sources which have reference sensors inside, they are calibrated in our calibration laboratory. And of course, we also have a protection device that protects actually the voice coils that are integrated in the source against overheating. And so it may happen that you have a too powerful signal that you want to feed into the source. Well, that device, the electronic protection device, limits and cuts that power and prolongs the life of the small voice coils inside the source. Actually, the process to obtain maximum output is every time when you choose a different spectrum for your excitation signal is by setting the gain just right below the level where that EPD is intervening or is being triggered. And then you're basically good to go. And since we are using those sources also at many different places, it comes with a flight case to pack it. And typically we use it with test lab software, with MIMO FRF, or with spectral testing. So I think this is most of the new things that I wanted to talk about. I hope you found the time you spent to attend worth the time, so for which I want to thank you. I do hope that you come up with a lot of questions. Not necessary right now, but you can also contact us in many different ways. So I'm really looking forward to your feedback.